Okay, so every function has a domain and a range, and we say the domain is the set of inputs and the range is the set of outputs, all right? Your domain is your inputs and your range is your outputs. The letter we give to inputs is X, and the letter we give to outputs is Y, okay? So when you can have any set of inputs and outputs that you want, only some of them are functions, okay? Any domain that goes with a range is a relation, but some relations are also functions. Some relations are also functions. Okay. So our job is to determine, given this domain and this range, is this relation a function? And the answer is no, because 3 has 2 outputs, and functions don't let you have 2 outputs, okay? So this is not a function. An element of the domain, we say, maps to more than one element of the range, okay? This domain, every element in this domain goes to a unique value in the range, so this is a function. Every element in this domain goes to a unique element in the range, so this is a function. And this one, this element of the domain goes to more than one element of the range. -6 goes to both -3 and 2. That is not a function. Okay. If I'm given a function, and if something says f of x, then you can take it to mean that that is a function that they're giving me. I can look at this function over different domains, okay? I can look at it over a discrete domain, which is just a collection of points. All right, so let's say I would like to look at this function over a domain of -2, -1, 0, 1, and 2. Okay, and I'm doing this in roster form, which is just another way of saying a list. All right, so I've listed out the elements of my domain. My range is built by inputting these elements of the domain into my function. So my range will be f of -2, f of -1. Okay, if I put -2 into my function, the absolute value of -2 is 2. So 2 is an element of my range. If I put -1 into my absolute value function, the absolute value of -1 is 1. So 1 is an element of my range. We'll continue on this way. 0, the absolute value of 0 is 0. The absolute value of 1 is 1, and I've already listed 1, so I do not need to list it again. 1 is already an element of my range. 2 going in, 2 as an input, the absolute value of 2 is 2, and 2 is already listed as an element of my range. So over this given domain, this arbitrary set of points that I chose, the range is going to be 2, 1, 0. Okay, this is called roster form, where you list a set of numbers, and we determine a set of numbers by this curly braces thing. Okay, a mapping is a way to specifically show which values go with which elements of your range, which values of your domain go with which elements of your range. You do it by forming 2 circles, like we saw in the previous slide. This is the x values, or the members of your domain. These are the y values, or the members of your range. If I say in my domain I have -2, -1, 0, 1, and 2, I don't know why I had to make this mapping the smallest mapping possible. Let's make it a little bigger, shall we? Here. All right, let's try one more time. Sorry. Whoop, that's better. Okay, if I have -2, -1, 0, 1, and 2, okay, as elements of my domain, and I already calculated the elements of my range, I'm going to list them in order. 0, 1, 2. Well, I can map which elements of my domain go with which elements of my range. So I would say, to complete this mapping, that -2 maps to +2, because f of -2 is +2. -1 maps to +1. 0 maps to 0. 1 also maps to +1. And 2 maps to +2. So this is a mapping of this discrete domain that I chose. Okay? I can also graph this discrete domain. I can say, well, if I input -2, I get an output of +2. So I put a point there, -2, +2. When I input -1, I get an output of +1. When I input 0, I get an output of 0. When I input 1, I get an output of 1. When I input 2, I get an output of 2. You would be tempted to connect those points, but I only have data right now for these 5 points. So I only need 5 outputs. If you connect them, you're going to get an infinite number of outputs. So you keep them discrete, keep them just as points and not as lines. If we want to graph lines, then we're going to make our domain bigger. The largest domain and the most common domain that we graph things on is all real numbers. All right. We can denote all real numbers as the set R. Okay, that double-lined R means all real numbers. And if I wanted to graph h of x on the set of all real numbers, I would do what I did in Algebra 1. I would say, well, my y-intercept, my b value is 2. Remember, I have a slope here. My slope tells me move down 1 to the right 2, down 1 to the right 2, down 1 to the right 2, and then up 1 to the left 2 if you want to go backwards. So you have this line, all right, with a slope of -1/2. And I'm graphing it over the domain all real numbers. Okay, if I do that, then I'm going to take, my domain will be all the x's because it hits all the numbers from left to right. My range will also be all real numbers, or the set R, because these arrows go up and down. They're eventually going to hit all numbers from the bottom to the top on the y-axis, all right? So the range goes from bottom to top, and this line will eventually hit all of those numbers, okay? What if I restrict my domain? I say I don't want to graph this on all real numbers anymore. Instead, I would like to graph it on this domain, when x is greater than -4 and less than or equal to +4. So I'm going to start the same line, all right? It still has a y-intercept of 2. It still moves with a slope of -1/2. But when we get to 4 and -4, things get a little bit interesting. This function is saying that we want to be less than or equal to 4. So x is allowed to equal 4. Okay, it's inclusive of 4. So we're going to put a closed point right there. Okay, but x is greater than and not equal to -4, which means that it can go all the way up to, but not include -4. So we denote that with an open circle. We say x is greater than -4, but it does not equal -4. So this line goes in between our x values of -4 and +4, but it is open at -4 and it is closed at +4. That's my restricted domain. My range goes from bottom to top. What is the lowest y value I have? All right, the lowest y value I have here is 0. Right here, let me change colors. Right here is the lowest that this function goes, and that is 0. So we say y is going to be less than 0. It is also going to equal 0 because this is a closed point right here at the bottom. Okay, the highest that y goes is right here at 4. But note, see this open circle right here? I'm not, oops, I'm moving it around for some reason. I'm not allowed to equal 4. I'm only allowed to go up to 4. So we say the range means, or we would denote that by saying it is less than 4, but not less than or equal to 4. This last one has a discrete domain. I have listed a set of specific points that I would like to graph. All right, I would like to graph an input of -4, and when I find h of -4, I'm going here to this h function, Negative half of negative 4 is positive 2, and 2 plus 2 is 4. So negative 4, 4 is a point that I'm allowed to graph because 4 is an output for negative 4. Negative 1, I'm going to now look for h of negative 1. Negative 1/2 times a negative 1 is positive 1/2 plus 2. So at negative 1, I'm here at 2.5, and I'm just going to estimate where that half is. At 0, I have 0 plus 2, which is 2. And at 4, I have a negative 2 plus 2, which is 0. Okay, and again, I'd be tempted to connect those points, but my domain is only asking me for these 4 points, not the entire space between them. Okay, so this second point is between, or this second graph is between negative 4 and 4. This one is just listing out specific values: negative 1, negative 4, negative 1, 0, and 4. That's it. So the range of this is 0, 2, 2.5, and 4. Okay, oops, that should be squiggly. Now, a natural domain is something that's unrestricted. So this first example is this function h of x on its natural domain, which is typically all real numbers. Okay, this second one is a restricted continuous domain because there's a line connecting all the points, so it's continuous from left to right. And then this third example is a restricted discrete domain. The domain is just a collection of points and it is not connected by a line.